Ladies and gentlemen, good morning. Today I would like to present to you some of the recent progress in MFTG, that's Meaningful Type Game Theory. So for those who are new, who are joining us for the first time, I will define what an MFTG is. What is an MFTG? So a meaningful type game is a class of games in which not only state action profiles of all the agent, all the players are considered, but also the distribution of state and distribution of action pairs. So why is this interesting? Well, it is interesting because it's considered, it goes beyond the expected utility maximization. It includes variances and higher order outcomes. So, for example, mean variance, quantiles, risk measures can be captured through this framework. So that's why it's the more interesting applications in different areas, in engineering, in finance, and of course in psychology more recently that we have been doing and so on. So here I will present to you a PID system, a partial integral differential system associated to the meaningful type games. So here is the setting. We consider a finite number of agents, let's say I, and for each agent, small I in big I, there is a certain set of functions. Okay, so the terminal cost will be denoted by HI, the running cost will be denoted by LI, for the state dynamics, a certain coefficients will be defined, so B is a drift coefficient function, is a vector, sigma is a diffusion coefficient functions, that will be a matrix, and gamma is a jump rate coefficient function, that should be a vector, and B tinned is a birth rate coefficient function, that would be a vector, and D tinned is a death rate coefficient function, that will be also a vector, with appropriate dimensions for all those vectors. And so we have the distribution of states. Well, we don't know if it's a probability distribution, but there is a certain measure, positive measure, that solve a Fokker-Planck equation, and that will be given by those coefficient functions. There is a usual measure, positive measure, that's given by mu naught. Now, each agent I will be minimizing a long-term cost functional, and that will be given by the integrated value of the terminal cost in HI and the integrated value of the running cost. Now we integrate over time horizon of the game, that will be denoted by T naught and T1. Now T naught obviously need to be less than T1. Okay, so now let me tell you what makes this problem a mean field type game problem. The functions HI, LI, B, sigma, gamma, B tinned and D tinned are non-standard functions. They involve not only the state, but also not only the state and action, but also the distribution of the state and distribution of actions for some of them. So HI is a function of the state and distribution of state at the terminal value T1. Li is the running cost, the function of time, state, actions, distribution of state, and distribution of actions, mu and mu tinned. And the same thing for B, for sigma, for B tinned, for D tinned, and for gamma. All right. With that structure, you can, for example, include a variance, mean variance type of functions. Now, each agent I want to find AI, which will be the action of I, and the action will be profile is all the vector of AIs. Now, the long-term cost will be minimized by I, and this will be done without knowing the choice of the others. So we will lead to a system of optimization problems involve the interdependence between them. That's make it a game, and we want to solve an equilibrium of that fact. So let's introduce an equilibrium cost VI hat that will solve a Hamilton-Jacobi-Bellman equation, in this particular case, Hamilton-Jacobi-Bellman system of equations, and the Hamiltonian here is an integrated Hamiltonian. That's why we get a partial integral differential equation. And now we want to know existence of solution to this problem. We want to know what are the equilibrium costs that can be achieved, this set of ranges that the equilibrium costs could be, a kind of Folk theorem for MFTG, and we want, of course, to know a selection of efficient equilibria if there are many, and of course sufficiency condition for which the system has a unique solution. Although, even if the initial problem has multiple solutions, is there any condition such that the HJB equation has a unique solution? Is it well posed, ill posed, and something like that? These are open questions in the general setting, and there are particular cases that we have investigated and where we have results. Now, first, the coefficient functions B, sigma, gamma, btint, and dtint, we want them to be linear in the state, linear in the mean state, linear in the action profile, and linear in the mean action profile. The cost functions Li and Hi, we want them to be at most quadratic in the state, quadratic in the mean state, quadratic in the action profiles, and quadratic in the mean of the action profile. If that's the case, we lead to linear quadratic MFTG system, and there are solutions. We can transform the problem into a system of ODEs for which sufficiency condition for existence can be found. Now, beyond this class of linear quadratic games, we have recently found a class of polynomial problems, polynomial cost, where solutions can be also found. It means transforming the PIDE system into ODE system for which a class of reasonable conditions can be found for the existence and uniqueness. Now, what are those non-quadratic solutions that have been found recently? Well, it's involved polynomial case, as I said. It's involved trigonometric functions, for example, sine square, cosine square, and hyperbolic functions and related combinations of those. So now the interesting thing is that when you have these convex functions, you need some variational inequality to completion. So the convex completion method is needed, not just square completion, but convex completion. So that's the technique that we use to find explicit solutions or semi-explicit solutions. And the good thing with the semi-explicit solutions is that the ODE might be, in some cases, might be easier to handle. So beyond that, everything is open. So we welcome everyone to contribute in this exciting area so that more applications can be understood. Thank you for your attention, and see you soon on MFTG.